Okay. Okay. Okay, we'll wait for 5 more minutes.
Yes.
Okay. Actually, Arsh K10 is trying to connect, but he's in offline. Arsh K10.
Sir?
Another student, Arsh K10, is trying to connect,
Okay,
but
okay.
he's in offline.
I'll
He is in offline. You
yes, sir.
ask,
I'll call him, sir. I'll call him.
ask him to connect
Yes,
the
sir.
net.
Yes, sir. Yes, sir. Hello. Ash. Hello. Hello, Ash. Yes, sir.
So, in this session, just we will discuss about the numericals related with the arc suppression coil or Peterson coil.
Okay, sir.
Actually, we have discussed the theory related with the arc suppression coil already. I think you might have remember that.
Yes.
So,
Yes, sir.
we used to use a coil, a resonating coil with the tappings. By changing the tapping, it is possible for us to nullify the capacitive current. By adjusting the fault current, you can nullify the capacitive current. That is the
Yes.
main idea of this arc suppression coil. Okay. So related to that, we'll see some numericals. And this derivation also we have already discussed. So the main aim is to nullify the capacitive current with the help of fault current. So here the fault current is defined as V phase by XL. That is per phase voltage divided by the total impedance of the system, particularly reactance, assuming resistance as minimum. Hello?
Yes.
Yes.
Yes, sir. Yes,
So,
yes.
yes, IF is equal to V phase by XL. And similarly, we have derived that IC, which is nothing but 3 V phase by XC. This we have derived it. So now we want to adjust the L of the that resonant coil such that your IF should be equal to IC. Then only the complete nullification of the capacitive current will take place. So if you equate IF is equal to IC, there is a mistake here. It is IF. It should be IF. IF is equal to IC. Then V phase by XL is equal to 3 V phase by XC. In that case, L can be derived as 1 by 3 omega square C. So related with the suppression coil, arc suppression coil, what is the formula you should remember is either XL should be equal to 1 by omega C or L should be equal to 1 by 3 omega square C. Inductance or inductive reactance. Okay. So this formula you have to remember like L is equal to 1 by 3 omega square C. Okay. So let us
Yes, sir.
start with a numerical. Calculate the reactance of the Peterson coil suitable for a 33 kilovolt three-phase system transmission line having the capacitance to earth of each conductor as 4.5 microfarads. Assume the supply frequency to be 50 Hz. So they have given the per phase capacitance is given. So we want to find the reactance, not the inductance. The question asked is reactance. Calculate the reactance of the Peterson coil. So reactance is nothing but XL is equal to 1 by 3 omega C. If it is asked inductance means, then it should be 1 by 3 omega square C. But since it is asked reactance, so directly you have to substitute the formula. That's all. Very simple 2 steps problem. XL is equal to 1 by 3 omega C, and omega is nothing but 2 pi f. We know that angular frequency, which is nothing but 2 pi f. So we can substitute the f is equal to system frequency, f is equal to 50 hertz, and C is also given, per phase capacitance is given 4.5 microfarads. So once you substitute those values, the reactance of the Peterson coil or arc subtraction coil can be calculated. It is 235.8 ohms. Are you able to understand? Hello?
Yes. Yes, sir.
Okay. Yes, sir. So we'll move on to the next one. Actually, only 2 are connected. What about the remaining? I don't know. Okay. So next one is a 230 kilovolt 3-phase 50 hertz 200 kilometer transmission line has a capacitance of 0.02 microfarad per kilometer per phase. Calculate the inductance and the kVA rating of the Peterson coil, neutral earthing, the above system. So here what are the given data is, they have given the transmission line length as 200 kilometers and the rated voltage is 230 kilovolts 3-phase. Capacitance per phase per kilometer is 0.02 microfarads. So what we have to do is, first you want to calculate the total capacitance per phase for the whole length of the transmission line. That is the total distance into the capacitance per phase per kilometer. You have to multiply. That is 200 into 0.02. Okay. So it will be equal to 4 into 10 power minus 6 farads or 4 microfarads. Now the question asked is, we want to find the inductance, not the reactance, inductance. If it is a reactance, then the formula is XL is equal to 1 by 3 omega C. But since they have asked it is inductance, L is equal to 1 by 3 omega square C. Just from that XL is nothing but omega L. You have to take that omega this side. So it will become 1 by 3 omega square C. Once again the same thing, omega is nothing but 2 pi f. So you can substitute that value and you can calculate the inductance, which is nothing but 0.85 henries. Okay. So the next question asked in the same problem is, we want to find the kVA rating of the Peterson coil. So what is that kVA rating means? Very simple. It is nothing but the per phase voltage into the current, maximum fault current at that moment flowing into that particular coil, Peterson coil or arc suppression coil. So what is the current that is flowing through the Peterson coil or arc suppression coil? You can once again verify this diagram. So this is the arc suppression coil. In this coil, the current that is flowing is nothing but IF. And we have already defined what is that IF. IF is nothing but V phase by XL here. V phase by XL. So with the help of V phase and XL, we can calculate the IF. That is what here they are doing. See, V phase is nothing but the line to line voltage is given as 230 kilovolt. So per phase value will be line to line voltage divided by root 3. That is 230 into 10 power 3 for kilo 10 power 3 divided by root 3. This is per phase voltage divided by the total impedance. So now you can calculate the impedance of the Peterson coil with the help of the inductance which we have already calculated. So the already calculated inductance is 0.85 henries. Thereby we can calculate the XL is equal to 2 pi FL. So 2 pi, F is 50, L is 0.85. Substituting this, you can get the fault current which is going to flow through your arc suppression coil. Now in the same manner, already we have calculated the per phase voltage, but here they are once again explaining the per phase voltage, which is nothing but line voltage divided by root 3. Line voltage is 230. So usually, no need to confuse while going through the problem. If they define a three-phase system with some voltage magnitude, that voltage magnitude represents line to line voltage RMS value. Okay. In case if it is a per phase voltage, they explicitly they will define that it is a per phase voltage. Without any definition, if they are mentioning a voltage, means in three phase it is nothing but the line to line voltage, that to RMS value, not the peak value, not the instantaneous value. Okay. So that 230 divided by root 3 will give you the per phase in kilovolts. So if you multiply it by 1000, you will get the magnitude, actual magnitude. So now you can rate the Peterson coil in terms of kVA. See, they have mentioned it is in terms of kVA. If you multiply these two, that is your fault current and the per phase voltage, you will get the VA rating of the Peterson coil. After getting the VA rating, if you divide it by 1000, you will get the kVA rating. That's all. Okay. So that is what they are doing here. V phase into IF, which is nothing but already we have calculated the V phase into 500 into 1 by 1000. 1 by 1000 is to convert that VA into kVA. So this much kVA, 66,397 kVA. Are you able to understand? Hello?
Yes.
So, okay.
Yes, sir.
We'll do another, okay, we'll see that another problem in the same thing. A 50Hz overhead line has line to earth capacitance of 1.5, 1.2 microfarads. It is, it's not visible, 1 minute. Yes, it is desired to use earth fault neutralizer. Don't confuse with this word. The earth fault neutralizer is another name for the Peterson coil. Arc suppression coil, or Peterson coil, or resonant coil, or earth fault neutralizer. So many names are there for that particular resonant coil, because that is very important thing, particularly the neutral counting method. So for this, determine the reactance to neutralize the capacitance of 100% length of the line, 90% length of the line, and 80% of length of the line. This is nothing actually. We want to calculate the XL for three different distance for 100% line, 90% line, and 80% line. So the formula is same, that is 1 by 3 omega C. In this, only the C will vary for the three different lengths, because capacitance is given as a distributed capacitance and its value is 1.2 microfarads. Okay. So for 100% it is 1.2 microfarads. Then for 90% it will be less than that. How much means 0.9 into 1.2. That is what here they are using in the place of C. This is for 100% line, because they have mentioned that the overhead line has line to earth capacitance of 1.2 microfarads. What is that meaning is, for the whole 100% line, its capacitance is 1.2 microfarads. So for 90% line, if you want to calculate the capacitance, it will be 0.9 times C. So that is what here they are correcting that formula. Formula is same, only the capacitance value is going to change for a different length of the line. For similarly for 80% it will be 0.8 C. The remaining and all it is same, just we have to substitute the values of the frequency and the capacitance. That's all. You can get the reactances value, different reactances value. Okay? Are you able to understand?
Yes, sir.
Okay.
Yes.
Yes, sir.
Okay. I'm opening another PDF just to discuss a problem related with the double line fault. In class, we have discussed, I think, two problems in line to ground fault, which is very important related with the fault analysis. So here we will see this double line fault problem. Are you able to visible? Is it visible for you?
Yes, sir.
This PDF?
Yes, sir. It is visible, sir.
It is handwritten only. I will read that because you cannot understand my handwriting. Find the subtransient currents. Question is, find the subtransient currents and line to line voltage. So you want to find the fault current, actual fault current, and line to line voltage at the fault under subtransient conditions when a line to line fault between B phase and C phase occurs at the terminal of the generator rated 20 MVA, 13.8 kilovolt, and has a direct axis subtransient reactances. What is this direct axis subtransient reactance? Means it is nothing but positive sequence reactance of 0.25. The negative sequence reactance negative and zero sequence reactances are 0.35 and 0.1 per unit respectively. The neutral of the generator is solidly grounded. Okay, it is not grounded through any other thing, it is solidly grounded. Of course, actually no need to worry about this solid neutral grounding for double line fault, because
Yes, sir.
zero sequence circuit won't takes place in the calculation of double line fault. I think you might have remember that the sequence network will
Yes.
be only positive and negative sequence will be there for double line fault. For single line to ground fault, all the sequence networks, positive, negative, and zero sequence networks will be connected in series. For double line fault, positive and negative sequence networks will be connected in parallel. For double line to ground fault, positive, negative, and zero sequence will also be included. All these will be connected in parallel. Okay. So here,
Yes.
for double line fault, there is no zero sequence, so no need to worry about the neutral grounding. Anyway, they have given, it is mentioned as it is solidly grounded. And we want to assume that the generator is unloaded and operating at the rated terminal voltage when the fault occurs. So neglect the resistance. So why they have given the word neglect the resistance means no need to confuse with the impedances. So in the place of impedances, you can assume it is only reactance, as resistance is negligible. Okay. So the diagram is drawn here.
Yes.
You can see the diagram. VPF is nothing but your pre-fault voltage. It is the pre-fault voltage. So this is the positive sequence network. That is along with the VPF Z1 positive sequence impedance. Of course, here it is nothing but only reactance J0.5. No real part is there. There is no real part. Z1 is equal to J0.25 per unit. It is given. Similarly, this is the negative sequence impedance. Okay. So VA1 is the terminal voltage across the positive
Yes.
sequence network, and VA2 is the terminal voltage across the negative sequence network. So the current IA1 and the IA2 are equal, but they are in opposite direction. So it can be written as IA1 is equal to minus IA2. So what are the given data is, one is positive sequence impedance, that is reactance, and negative sequence impedance. Then the rating of the generator 20 MVA and voltage rating is 13.8 kilovolts. So using the given capacity of the generator and the voltage, you can calculate the base current. So how to calculate the base current? Just the MVA divided by root 3 into the current 13.8. So you'll get a base current of 836.7 amps for this case. Okay. Now you can solve any one current from this network. You can solve either IA1 or IA2. So IA1 is nothing but EA divided by Z1 plus Z2. So EA is nothing but here EA or VPF. Both are same. EA or VPF. It is same. Its magnitude is 1 at an angle of 0. And if you add Z1 and Z2, where Z1 is nothing but 0.25 and Z2 is 0.35. So total it will be J0.6. So 1 divided by J0.6 will become minus J1.667, or in a rectangular form, sorry, in the polar form, it is in rectangular form already. In the polar form, 1.667 at an angle of minus 90 degree per unit. Now you can easily calculate the IA2 from IA1, because you know the relation between IA2 and IA1. IA2 is equal to minus IA1. So thereby IA2 is equal to J1.667, which is nothing but 1.667 at an angle of 90 degree per unit. And IA naught, surely it will be equal to 0, because as there is no zero sequence network, no zero sequence current can flow. Any fault without ground connection, there won't be any zero sequence current. So now you can calculate the fault current. Here the fault current is nothing but either IB or IC, because B and C phase are shorted. So you can write the relation between the phase current and the sequence current. IB is equal to IA naught plus A square IA1 plus A IA2. You know what is that A operator? I think. Hello.
Yes.
Alpha.
What is
Yes.
it? What is it?
Yes,
A?
sir.
It's alpha.
What is it? Alpha or A? Here I am mentioning it as A, small a. What is it? A operator or alpha operator?
1 angle 120.
Yes. So using that you can calculate, substitute that one, and you can
One
calculate
angle
the.
120.
Yes. You can calculate the value of IB. So the value of the IB, the fault current in per unit, it is nothing but minus 2.886. Okay. Similarly, the IC will be just opposite to this. So minus won't be there for IC. IC will be the same value, 2.886 per unit, but plus 2.886 per unit. So if you want to calculate the actual value, you should multiply the per unit value into 837, where 837 is the base current. If you multiply that one with your
Base
per
current.
unit base current, already we have calculated the base current. I think I told you the base MVA
Yes.
divided by
Yes.
root 3 into 13.8. You will get the base current. So now here you want to
Yes.
multiply the per unit with the base current. So here minus 2.886 into 837 will give you 2416, 2416 amps or 2.41 kilo amps. Similarly, IC will be to same thing, but angle is different. If you assume this as 0, this will be 180 degree, just opposite, just opposite. So we can declare the fault current for this case, double line fault for the given conditions, it is 2.416 kilo amps. There is another question also asked in this problem. After finding the fault current, we want to calculate the line to line voltage. What is the line to line voltage? That is, what is VAB, what is VBC, what is VCA. All those things we have to calculate. Now to calculate those things, we should know what is the phase voltages, corresponding phase voltages, VA, VB, VC. All those voltages we have to calculate. In order to calculate that one, we need to calculate the sequence voltages. So what is that sequence voltages? Here itself we have already discussed in the parallel combination itself. VA1 is the positive sequence voltage, terminal voltage. VA2 is the negative sequence voltage, where VA1 is nothing but VPF, pre-fault voltage minus IA1 Z1, where VA2 is nothing but IA2 Z2. Clear? And what about VA naught? It will be equal to 0. Why? Because IA naught will be equal, it is 0. Zero sequence
0.
current is 0. Thereby, VA naught, which is nothing but minus IA naught Z naught, will become 0. Okay. So using this formula, VA1
Yes.
is equal to either EPF or VPF or EA. Okay. Minus IA1 Z1. You can calculate the value, and here from this parallel combination easily you can say VA1 is equal to VA2 because they are connected in parallel. Both the positive sequence network and negative sequence network are connected in parallel, so thereby they will be equal. So once you calculate either VA1 or VA2, you can share that value among VA1 and VA2, both will be equal. So here it is nothing but 0.583. Now, after calculating the sequence voltages, you should calculate the phase voltages using this relationship between the phase parameters and the sequence parameters. So using this relationship, you can calculate the VA, VB, VC. For that, once again, you should know what is this alpha or A, 1 at an angle of 120. So after using that, you can calculate the VA, VB, and the VC. So once again, these VA, VB, VC all are in per unit, and these are nothing but the respective phase voltages. VA is the phase voltage of A phase, VB is the phase voltage of B phase, and similarly VC is nothing but the phase voltage of C phase. Now, actually, what is the question asked? This not the phase voltages. The question asked is line to line voltages. So how to
Line
find that?
voltages.
Yes, line to line voltage, which is nothing but VAB, VBC, VCA. So in order to calculate VAB, you should subtract VA minus VB. That is the usual procedure. Okay, right? VA minus VB.
Yes.
But this minus is not a normal algebraic subtraction. It is a vector subtraction. VA minus VB. So if you subtract these two, you'll get the value. Similarly, VB minus VC. Similarly, VCA, VC minus VA. So once again, These values, whatever we have calculated, VAB, VBC, VCA, all are in per unit. And you can see that VBC is 0. Without doing all those calculations, by seeing the problem itself, we can declare VBC will be equal to 0. Why? Because line to line fault occurs in between B and C. It is dead short circuited. So the line to line voltage between that will be 0 at that point. Okay. So after finding these values, you have to multiply it by the respective base voltages. Okay, to get the actual voltage, because this is per unit. If I multiply this per unit value with the actual voltages, then only I can get the, sorry, with the base voltages, then only I will get the actual voltages. But now the question is, see, the given value base voltage is 13.8 kilovolt here, 13.8 kilovolt, which is the line to line voltage. This is the base voltage and this is the base MVA. But this base voltage is in terms of line to line voltage. But to calculate the actual value phase voltages, per unit voltages, directly you should not multiply this 13.8 kilovolt. Instead of that, you should convert this base line to line voltage to phase voltages. How will you convert? Very simple. Same 13.8 kilovolt divided by root 3. If you divide it by root 3, you will get 7.9 kilovolt, which is nothing but your base voltage for phase to ground voltage. That is phase voltage. Can you understand? 13.8 kilovolts is the line to line voltage
Yes.
base value. 7.9 kilovolt is the phase to ground base value. Surely you should use only this value 7.9, not the 13.8 to calculate your actual value. Why? Because even though we are naming this VAB is nothing but the line to line voltage, we are calculating that one with the help of phase voltages only. VA is the phase voltage, VB is the phase voltage. Similarly, for calculating VCA, VC minus VA, where VC is the phase voltage and VA is the phase voltage. That is why after calculating this value, in order to convert this per unit into actual value, surely we have to multiply it by the base phase to ground voltage, which is nothing but 7.97. So you will get 13.94 at an angle of 0 kilovolts, VAB, VBC is 0, and VCA is 13.94 at an angle of 180 degree kilovolt. Okay. Can you, are you able to
Yes.
understand? Okay.
Yes, sir.
Yes, sir.
Okay. Actually, I plan to take another important numerical related with the IDMT relay, design of IDMT relay, but only 2 are there. So we will plan for any other session for to explain that. Okay. Is
Yes.
it okay? Okay. Any doubt is there? Any doubt? Are you having any doubt? Is it
No,
clear?
sir.
Uh,
Yes, sir, it is clear.
The Ketan?
Yes, sir, it is clear.
Ketan is there? Hello, Ketan? Arsh Ketan?
Yes, sir.
Is it clear?
Yes, sir, it's clear, sir.
Okay, thank you.
Yes, sir, it's clear.
Okay, bye. We'll
Yes,
see.
sir, it is
Okay, we will see in the next session. I will take another session.
Okay, sir.
Okay,
Yeah, okay, sir.
okay, but thank you.